In our last video on the finding density by displacement, we demonstrated the density of a glass stopper as having 5.7 grams per centimeter cubed density. So what we want to do in this video is demonstrate how the density of an object can be utilized to make predictions, which is, of course, what science is all about. Now, what we can use is use skills that we've learned in class in order to do this. So I'm going to give you some sample problems and demonstrate just how easy this is, utilizing this property of matter, this physical property of matter of density. Now, there's a couple things that we want to learn right off the bat that we're going to need to remember throughout the course. And that is one thing about units of measurement. But let's read the problem first, and this will stick out real quick. So we have the density of our glass stopper, which was 5.7 grams per centimeter cubed. That's what we got last time from the other video where I demonstrated how to find that density of the glass stopper. That was our final answer. So if we use the same glass, or if the same glass was used to make another glass stopper, so we have another glass stopper, we know it was the same glass, and we've gotten the volume of that glass stopper as being 1.23 milliliters in volume. What's its mass? Now, if you read this problem and you don't know some information, this might throw you off, okay? So we have the volume of our glass stopper, but we don't have its mass, right? We've got the density, right? And it's in grams per centimeter cubed. That might throw you off a little bit, but one thing that you need to learn right off the bat and understand is that 1 centimeter cubed, 1 cubic centimeter, is equal to, and we should have learned this way back in standards of measurement. If we didn't pick it up then, we want to know it now, is the same exact as a milliliter. They are identical, okay? We want to remember that when we learned our standards of measurement, that centimeters cubed is our SI system way of measuring volume. And milliliters is the metric system, right? So centimeters cubed is the SI system, and the metric system is milliliters. And a lot of times in science we use them both. We try to stick with the SI, but milliliters are just so common that we tend to use them both, and they're very much what's all over our instruments for measuring. So when it comes to volume, for some reason we just can't get away from the metric system. So we see these two all the time. Milliliters are equivalent to centimeters cubed. They're identical, okay? So really this is of no consequence because these are the same thing, okay? Now, how do we use, how do we do this problem? So we have the density of a glass stopper, and it's 5.7 grams per centimeter cubed. What we want to understand right off the bat is what density is, and we should remember it's what we call a derived unit, right? So it is the combination of two units mathematically put together. And it's the same thing as saying that 5.7 grams of our substance equals 1, we could say centimeter cubed, but since we're using milliliters down here, why don't we use milliliters? Equals 1 milliliter of our substance. And what does that look like to you? I hope you say a conversion factor. Remember, our problem-solving strategies, what we're always trying to do in our first step is to understand the problem and to make it more simple, right? And that is what I'm doing right now. I'm making my problem more simple and easier to understand. So when we have a density problem and we are given the density and we're missing one of the values, either the volume or the mass, but we're given the other, guess what we can do? We can convert, because density is a conversion factor. And that's what we mean by using density to make a prediction. we're predicting what the mass will be given the volume, because we know that the density of the substance will never change. The density of a substance is its physical property, and it will always be the same as long as the substance isn't changing like its state of matter, right? If the glass is the same temperature, right, it's always going to have the same density. So what do? We use this to convert from our milliliters to our grams, right? We're starting with milliliters. We want to get to grams. That's the mass. What is the mass? So I'm converting from milliliters to grams, right? And this is our conversion factor, the density. It's that simple. It's a one-step conversion problem. So we just say 1.23 milliliters times, milliliters goes on bottom, grams goes on top, 5.7 for every one. Cancel out our units. It's 1.23 times 5.7. And I get 7.011, and that's grams for every milliliter. And I need to make sure I do my sig figs right. So I got 2 here, and let's do a different color. 2 here and 3 here, so I should have 2 in my problem. So it's going to be 7.0 grams per milliliter. Oops, not grams per milliliter. What am I talking about? This isn't density. We're solving for mass. There we go. Grams. 7.0 grams. And that's how you do it. These are conversion problems. I think you're going to find very quickly that pretty much most problems we do in this class are going to use dimensional analysis. So, we can just as well see this happen the other way around. Okay, if we're given the density, what is the mass if we, or what is the volume if we know the mass? It's the same thing, okay? We know the density is a conversion factor. This time we have the mass, we're going to convert to the volume. So I'm going from grams to milliliters. So 28.67 grams. This time it's just the grams is on the bottom of our conversion factor. And then the 1 milliliter goes on top from our conversion factor. And so we divide. And that's the only difference when we're going the other direction. We'll still have 2 significant digits because of our conversion factor. In this case, is a measured conversion factor. And I get 5.0298 milliliters. And so with 2 sig figs, that stays the same, 5.0 milliliters. And so that's how we use these densities as conversion factors to make predictions, right? Now, this brings us to another discussion. The 2 vocabulary words that we want to know. Let me get by there. And that is this. And you saw this word at the very beginning of our displacement by density video, or density by displacement video. And that is, we have 2 types of properties of matter. Not just chemical and physical, we have other classifications as well. We have what are called intensive, and extensive properties of matter. And what you saw at the title screen of our finding density by displacement was that density was an intensive property of matter. And what an intensive property of matter is it's a property of matter that does not change or is unaffected by the amount of substance present. So something like density. No matter how much of the substance you have, its density will always be the same. Right? Its color. No matter how much sulfur I have, it will always be yellow. Right? Okay? Its smell. The strength of the smell may change, but its smell will always be that type of smell, right? These are intensive properties of matter. Extensive properties of matter. Let's get a different color. Oh, that is bright. Horrendous. There you go. Properties, and you can guess. Properties of matter that are affected by the amount of substance present. Okay, so the mass is very simply an extensive property. The more substance you have, the more mass it's going to have, right? That is an extensive property. I mean, these are the simple ones. Volume, one property is called electrical current. That's how much electricity can run through something. If it's conductive, the more substance you have, the more electricity is going to be able to run through it. Okay, that's one example. These are extensive properties. So the more you have or the less you have, the property that you're studying will change depending on how much you have. Okay, and so that's why you bring this up at this point, is because what we like to deal with for studying and comparing substances are the intensive properties, because we don't want to use properties that are going to change on us depending on how much we have. We want to use properties that are going to be constant, right? So density is a great one, or color or smell can be pretty good too, but we like ones that we can give numbers to. Okay, that's why density is such a good one to use. A great example is the density of water. Water is a standard. The density of water we use actually as a standard a lot. So we know that the density of water at room temperature is 1 gram for every 1 milliliter. You should know that. You should have that memorized. That's something you should know from other classes, other science classes you're taking, right? Density is 1 gram per 1 milliliter at room temperature. We have charts that we use as that temperature changes. So as it goes up and down, this number, we change the gram amount. Will go up or down, right? So temperature will affect the density, but at a constant temperature, we can always depend on water being 1 gram per 1 milliliter. And we can use that to our advantage in many ways, as we'll find out very soon.